second version. So we're going to see there's two different types of chi-squared testing as we go through this thing. We will finish the whole section of chi-squared. It doesn't take that long. All right, so what is a chi-squared test? Anybody taken AP biology before? All right, so you guys have done this before. In some form or facet. I don't know exactly how because Mr. G has zero experience in AP biology. But I do know that in AP biology, you have done chi-squared probably to test whether or not things are dependent or independent as far as traits and stuff. That would be my guess, completely unscientific guess. All right, so it is used to test the counts of categorical data. So your first two blanks are counts and categorical. The word counts is the most important thing with this. We're going to see later that if you don't have counts of something, then chi-squared is not going to be your friend. We don't even need to worry about it. There are three types of chi-squared test officially. The first type that we're going to talk about is a goodness of fit chi-squared test. This is testing univariate data. And as we learn when we go through this, we're going to test to see if it matches our expectations. So we're going to be doing basically hypothesis testing with these numbers. The other type is a independence or a homogeneity test. I always mess up that word. And this is where you're looking at bivariate data. So who remembers the difference between univariate and bivariate? Just to make sure we're all on the same page. Univariate is one set of data, and that means bivariate is, very good, Mr. Laura. So two sets of data. So univariate, we just have our one, and we're going to have what we expect from it. So we're still comparing two things, but we're looking at one set of data. Whereas the last two with bivariate, we have two completely different sets of data, and we're comparing them together. Are they dependent, independent? Do they match? That kind of. All right, so that is the plan for our chi-squared testing. All right, so what does the distribution for the chi-squared look like? I don't know if you guys have ever seen the graphs for chi-squared or not, but it is skewed to the right, meaning most of the data is centered on the left side of the graph, and then it tails off to the right side. Different degrees of freedom will have different graphs or different curves. As we increase, our degrees of freedom, our curve will shift more to the right and become more normal. So another example of where having more categories or having more sample size or having more stuff is more accurate than less. Not that it's impossible to do less. But it will work. All right, so here's a picture of it. That's when the degrees of freedom are 3, very skewed right. As I increase my degrees of freedom, the graph starts to level off and shift toward the right, becoming more normal. So whereas the degrees of freedom of 10 are, the graph's looking pretty nice. But it works with all three of these, all right? So when we're doing a chi-squared test, we're going to have assumptions, just like we did with the hypothesis testing, just like we had with the confidence intervals, just like we had with everything else. If these two things are met, then we can go forward with our chi-squared testing. If they are not met, then officially we're not supposed to. So as always, you guys should see a theme on all of this stuff. What's the first most important thing for any one of these? That there's randomness. Okay. So little did you know way back in October when we talked about sampling design that randomness was going to be so important, but it is. If there's not randomness, then there's bias, then our results are skewed or trash or whatever. So randomness, very important. So this will be the same as before, simple random sample of whatever we're talking about. The other thing is new. We need to make sure all of our expected counts are greater than or equal to 5. So we're going to talk about how to determine what your expected counts are. There's different ways to do it depending on your data set, but you will have to verify your expected counts. So this will be the little more tedious part of this test is you have to list out all of your different expected values and you'll have to check. Are they all greater than or equal to 5? So that's what I have to do with your guys' survey before we can use it. All right, there's a fancy formula for chi-squared testing. If we were doing this by hand, this is the formula you would have to use to find your chi-squared value. You would take your observed data from whatever data set you're looking at, minus the expected value you thought you were going to get, square it, and then divide it by the expected value. And you would do this over and over again for each of your categories and add them up. So this is very similar to when I made you guys do the variance, like what, the second day of school, third day of school, whenever I tortured you guys and made you write out the whole process for variance. Same thing here.
Standard deviation.
You're exactly right. And I was just going to say, then it leads to standard deviation. If we take the square root of this, it would be the standard deviation. Very good, Skylar. Nice. So you guys do remember some things from the fall. All right, so steps for our chi-square test. What do we got to do here, Mr. G? Well, very similar to our hypothesis test. Number one, you need to state your hypothesis in words, be able to identify what the heck you're even testing. Number two, we have our two assumptions we need to check. Is it random? And all of our expected counts are greater than or equal to 5. Don't forget your test name. This first one that we're talking about when we go through it is going to be the goodness of fit chi-square test. The second one and the last part of the notes will be for independence. All right, so you'll have to make sure you're picking the right one. For calculations purposes, again, we have our nice, lovely technology here that we love and adore. So we just need to put our 4 values up there: the chi-squared value, the degrees of freedom, the p-value, and the alpha. You don't have to do it by hand and write out the formulas and do all the steps. Thank you. So just make sure that you do that. I will show you guys here in just a second how to use the program so you're all on the same page. And then, of course, a conclusion, which looks just like your hypothesis test. Since my p-value is greater than, less than alpha, I failed to reject, whatever. There isn't enough evidence to support blah, 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 blah. Right, so your conclusion sentence should be very familiar at this point. All right, so let's talk about the first one. There's 2 types of tests we're going to go through. Yes, there's 3 different things we can do with it. But the first type of test is the goodness of fit test, or abbreviated GOF in your calculator. So this is the one that uses the univariate data. We are going to see how well our observed counts fit with what we expect. All right, that's the whole purpose of this one. Our degrees of freedom for this problem is going to be whatever the number of categories we're looking at minus 1. So you'll know how many categories you're looking at because the word prompt is going to divide it into how many different groups of things that exist. So you just take 1 away from that, that's your degrees of freedom. And you can use, if you're doing it by hand, we're not going to use this function, but if you're doing it by hand, you can use a chi-squared CDF function to put it in as the lower value and put infinity in as the upper value, and then do degrees of freedom, and you're all set. You can find p-values. But we're gonna circumvent this process entirely, and we're gonna use the program that's built into the calculator where we just type in stuff and hit enter. But you could do the formula by hand and still use the calculator to find it. Or if you guys want to be like super old school fancy, let me show you something real quick, just to be that guy. On Canvas is the official. It has been officially loaded for you guys to look at. The official formula chart for the AP exam. So when you get your nice brand new AP exam, this is the formula chart you're going to get. You guys will recognize things like our regression stuff, right? X bar, Y. You'll recognize probability, everybody's favorite unit. You guys will recognize the formulas from last unit, number 7. And then down here at the bottom, you will have the Z table. All right, so you could do all your Z scores by hand now if you wanted to. Oh, Laura, I know you're so excited. You want to go back and do all those by hand. Just completely throw the calculator away and live in the glory that was the 1980s. Because you guys think it's so cool with all the music and movies. All right, we'll do the math from the 80s and see how much you like that decade. Here's your T distribution table. So you can also do your T testing from this one. Look how excited you guys are. And there's today's chi-squared. So if you want to do it that way, here it is. You just got to figure out your degrees of freedom, and you can figure out what all your chi-squared value is, and it'll tell you what your p-value is right there at the top. So exciting, so fun. I know that's what Claire's going to do when she gets home too. She's going to jump right in there and work those tables. So anyways, you will get all that stuff for your test. You can take those little nice tables, you can just set them to the side and just look at them and be like, don't need those. Until you meet that one professor in college who still does live in the 1980s. All right, so hypothesis. How are we going to write our hypothesis for this? It's right there in your notes. They should look pretty similar to what we've done before. The 2 things we're looking at here is our original assumption, our null, is that everything is what it's expected to be. Okay, so all proportions of whatever are equal to what we thought. So that should always be your original hypothesis. And then for the alternative, you guys will notice kind of what we're doing with this one. We're not looking for all of them to be different. We're looking for what? At least one proportion is different. So I don't know, I might underline that. I did on my notes, because that phrase, at least one, is important here. We don't care if they're all different or not, just that at least one of them is weird. That's enough evidence for us to say that we're off our expected proportions. So that's what we're testing for. During your notes, you don't have to write anything down, but I would underline that at least one part because that's important. Usually comes up at some point as a multiple choice question. All right, again, be sure to write in your context. So whatever is underlined gets replaced by whatever's in the word box. All right, let's do an example here. So it's an interesting topic. Does your zodiac sign determine how successful you will be? Fortune magazine collected the zodiac signs of 256 heads of the largest 400 companies. Is there sufficient evidence to claim that successful people are more likely to be born under some signs than others? So here's 256 randomly collected ones. Skylar's convinced that people who are Pisces are going to be the billionaires. Maybe he's also convinced that the poor Gemini and Libras are doomed to a life of middle management. I don't know. That's what he's convinced of. So what we're going to do is test this. Is there enough difference here from what we would expect to get to say that this is true? Or is it just numbers and it just happened to be that way because it was random? So before we start doing anything, we need to check our expected values and see what would we expect the numbers to be in every category. So how many would you expect in each sign if there were no difference between them? Because that's our original assumption, right? How many differences are there? None. So that means all 12 categories should be exactly the same. So this is just simple division. You have how many categories here? 12. And you have how many people? 256. So divide them. That makes sense where I got that number. So there is going to be a little bit of creativity here where you have to kind of figure out your expected value. So we would expect CEOs to be equally born under all signs. If all things being equal, that's what our original hypothesis is going to be. So we're going to use this number in a second, this 21.3333, when we do our formulas and calculators and all that kind of stuff. All right, how many degrees of freedom do we have? See who's been paying attention to my notes so far. All right. 11, thank you. I was gonna say supplement question. How many categories do we have? We have 12. So if we take one away from 12, then we have 11. So we got 1, 2, 3, 4, 3 different times. So we have 12 categories. Take one away. We're looking at 11 degrees of freedom. All right. So is everybody okay with these numbers before we move on? Because these are important that you know these two things. Otherwise, what you're going to type into your calculator in a minute is not going to work for you. So I should be mean and make you guys do it all by hand, but I don't want to sit here for 10 minutes and watch Connor write out the formula and then do all the division. So we're going to go straight to the calculator steps, but just know that they might ask you on the AP exam, you know, what you're supposed to do or which formula is correct. So it doesn't mean that that formula is not important. All right, so let's go through the whole thing. The space for this is very limited on your notes. So if you want to write some extra on a side piece of paper, you can. I squished mine in there. It's not pretty. But there's not much space as you're writing through this stuff. So just be aware that I know that the space is terrible. That's what Google does to our stuff sometimes. Let's start off with the name. What kind of test are we doing? A chi-squared test for goodness of fit, which means we're looking at univariate data. We're taking the CEOs and the signs they were born under and comparing it to what we expected them to. That's it. We're only looking at one set of data here. All right, so what are our two assumptions? That we have a simple random sample of CEOs, looking through my thing. Yep. Doesn't say it's officially random, but yep, looks good. And then the second assumption is all expected counts are greater than 5. I verified this. Remember, you have to verify it. We have to verify before we move forward that we have counts greater than or equal to 5, and ours is 21.3333. So we expect this many CEOs under each side, if all things being equal. Because obviously there's probably a lot more variables at play than just what month of the or what year, time of the year you're born. All right, assumptions are met. Let's do some hypotheses. So what is our original assumption? That the proportions of CEOs born under each sign are the same as the other. It's not fair that the Pisces have more numbers. That's not supposed to be the case. Or that the Gemini and Libra are short a couple. That's not right. So that's our original assumption. We're going to test, though, if the alternative is true, that at least just one of these groups, doesn't matter which one, is different enough than the others to say, maybe everybody should start planning on having Pisces babies if they want CEOs. All right, any questions so far on the assumptions, expectations, and or hypothesis? You okay with all this? Pretty straightforward, cut and dry, clear as mud. What you signed up for, the whole class is to write reports over and over again. Maddie, you warned your friends yet? I think sometimes they come in there like, we're just gonna do maths and graph all day, like for the first month. All right, so here's the calculation. So I'm going to show you guys how to get this in the calculator in just a second, but these are the 4 things you need to show in order to make your verification. You need to show the degrees of freedom, the p-value, the alpha, and the chi-square value. So on the notes you see right here, Ms. Nichols went through the formula. Now, she did not type it all in, but she went through all 12 categories and figured out their basically variance and came up with a chi-squared number. So this first one here is the Aries category. It's 23 minus the expected squared divided by the expected. And then she went over and did the Taurus, it looks like next. So that's 20 minus the expected squared divided by the expected plus a bunch of more, and then wrapped up with the Pisces number, 29 minus the expected squared divided by the expected. After all that math and doing it by hand, because I know Connor's super excited to try that, just kidding. She got a chi-squared value of 5.09375. So again, for those of you guys that think the 80s was like the best decade ever, well, there's your math right there to prove it. Go for it. Enjoy your time. We know degree of freedom from the categories. Now that you got this chi-squared value, you could go into the chart or the calculator, put it in as your lower limit, upper limit is infinity, 11's degrees of freedom. You'll get this for the p-value. I'll show you guys in the calculator. We don't even need this function. It's going to go right to the p-value for us. And then our alpha, unless otherwise stated, is 0.05. All right, so let's do some calculator work. There's a little bit of work involved in the calculator, but it's certainly not the formula. All right, so you grab the calculator, and the first thing you need to do before you go anywhere or do anything is make sure you have 2 lists set up with everything you need. So go to Stat, go to Edit, and you need to have lists. So I got to clear off my used list from earlier. Make sure you hit clear and not delete, or you'll be crying during your AP test. Don't hit delete, hit clear. So list number 1 should be what you observed. So I'm going to look at my little chart here, and I'm going to type in my 12 numbers on the observed one. Now, for this particular test right here, this example only, the order in which you type the observed does not matter, because they all have the same expected value. However, on our other examples, that may not be the case. The expected values might be different for each category. So you can't just mix and match willy-nilly. You got to make sure things line up or your test is going to be off. So I'm going to type it in, just going across Aries to Leo and then down the rows. You can do it whatever order you want, because this time the expected values are all identical. So there's no problem there. 18, 19, 24, 23, 22, and 29. All right, so I should have 12. I do. So these are all of my observed values. Come over here. We know what the expected value is for these. It's 21.3333. So you just got to make sure that gets filled in all the way down. And I'm sure there's a shortcut up that one of you guys can figure out, but I haven't been able to figure that yet. Now, this is tedious, yes, but this is simply, or a lot more simple than doing the whole formula. Trust me. Time yourself doing the formula if you don't believe. 29 is the very last category, yeah, for Pisces. So this is the observed, this is the expected. All right, so I'll give everybody a second. Make sure you got that in your calculator. Those of you guys that want to be adventurous, you're welcome to explore and see if you can figure out the program without me. But if you want to wait a second, I'm going to go to it. All right, now that we got our data put in there, we'll go to our favorite category, stat, and to all of our nice pre-programmed lists. So again, if you're going to do anything statistics, anything biology, anything psychology, anything calculus, anything like that in college, and you have one of these calculators, you are set. Like, this thing is awesome. All right, I can vouch for being a recent college student. You do not need more than this. Don't let somebody convince you that you need a TI-89 or a computer or anything. This is awesome, or something very similar to this. If you don't have one of these, or you have like an 83 or less or something, whatever, and you're looking for a graduation gift and rich aunt has too much money to spend, I know it's not exciting to get a calculator, but this will make your life in college much easier if you know how to use these things, because colleges more and more are allowing for calculators. And as you guys can tell with our last couple of units, it's a lifesaver to have these things right here with you. Otherwise, you got to do them all from scratch. Like you still have to show your work, but you know the answers, right? So that's kind of nice. Anyways, go all the way down to letter D. We're doing the chi-squared GeoF test, goodness of fit. All right, we will use the other one in a second. Right now we're on D. All right, you press enter, it's going to ask you which ones are your observed, which ones are your expected. So if you do everything in a normal order, then L1 and L2 should be covered. But you're welcome to change these if you got other stuff saved in there. And then the only thing you need to make sure you have correct is degrees of freedom. We said is 11 for this one. All right, once you're set, you hit calculate, ta-da, there's all your stuff. So there's 5.09375. Yay, chi-squared value. So you're going to make sure you write that down. You got to have that calculation. Remember, P stands for p-value. All right, so that right there is your p-value, 0.9265. That's a large p-value. So we already know what we're going to be doing with our decision. That's okay. We're going to get some weird p-values with chi-squared. Doesn't mean you did it wrong. And then degrees of freedom is 11. All right, everybody good? Anybody need help finding anything? Anybody stuck? Jessica looks super excited over here. Found it all, Jessica? Okay, so let's have a look-see at the conclusion. All right, since the p-value is larger than alpha, I would hope so, I failed to reject the original hypothesis. So before we write the rest of the conclusion, let's see what we said here. What we just said was, with all of our data in front of us, is that there is no difference in which sign you're born under. None whatsoever. Even though there was a weird 29 in Pisces and an 18 in Libra and Gemini, that was not weird enough, and at least one of these, to say that there's a different sign. So all the people that were just planning to have kids born under the sign Pisces so that their family can become future billionaires, don't worry about it. There's no difference statistically, according to this study. So have them kids whenever. I should run one of these, Connor, on the months that you're born and if you become an NHL player, because my son's convinced he's going to be. We'll see. Because there is in Canada, if you have your kids born like January, February, they're older because it all starts to go by what year they're born in. And so all these parents, and I guess for every sport it's different. But for hockey in Canada, they all try to have their kids in January and February. If they want their kids to be really good hockey players, because they'll all be the oldest in each year that they play in. So my son's August, so whatever. He'll deal with it. Anyways, now you know how to test what you expect versus what it should be. Any questions on this one? Easy enough, I hope. Hope you guys are getting the groove of this stuff. We're having a little fun with it now, maybe. I don't know. Maybe this is like the most tedious, boring thing you ever done in your life. But I like it. It answers questions. You can show how smart you are to your friends by just comparing data now, just for the fun of it. They won't know that you're right or wrong. All right, let's look at example 2. A company says its premium mixture of nuts contains 10% Brazil, 20% cashew, 20% almond, 10% hazelnuts, and 40% peanuts. So I buy a large can and separate the nuts. Upon weighing them, I find there are 112 grams of Brazil, 183 grams of cashews, 207 grams of almonds, 71 grams of hazelnuts, and 446 grams of peanuts. I wonder whether your mix is significantly different from what the company advertises. Why is the chi-squared goodness of fit test not appropriate here? So go to the very top of your notes. What's the first blank you guys filled in? So go to the very top of your notes. What's the very first blank you filled in? I need to have counts. Do I have counts in front of me? I have percentages, right? So can't do chi-squared if I have proportions. I got to have actual physical numbers. So instead of weighing my nuts, I don't know why I would weigh them. I should just count them. That's easy. Just grab them out, put them in the group. So if I do that, then I can switch this to a chi-squared. So I wanted to give you guys this example so you can see not everything broken into categories is chi-squareable, if that's a phrase. It needs to be specific counts of something that you can then compare to expected values of something. This is categorical data. Okay, so think way, way, way back into August when you guys were unsure about this class at school and everything was going to be. And we talked about the 2 types of data, categorical versus numerical. Categorical data, it's either you fit into it, yes, no, and that's it. Like we just count it. All right, we got 20 people that like Netflix, 14 people that like Hulu, 6 people that like Disney Plus, whatever. Same thing with the chi-squared. You're either a cashew or you're an almond or you're a hazelnut. There's no point in me doing averages and grams and all that stuff. Stick to categorical data. Make it So if I wanted to actually do a chi-squared test with this, I'd have to take all my Brazil nuts, put them in a pile, and then count how many I got, take all of my cashews, et cetera, et cetera. We did a really cool activity with this last year when we went to at-home learning. We had people go grab a thing of Skittles or M&Ms, and they did that. So they could count out, I have this many reds, this many greens, this many yellows, whatever. And had them go look online to see what they should have had, and then they did a chi-square test. This is what we're going to do with your guys' data that you're giving me. How many right-handed people I have, how many left-handed people I have. All right, so let's do another example of chi-squared goodness of fit. I'll let you guys take the lead on some of this before I put the answers up to make sure you understand it, and then we'll move on to the other type of chi-squared testing. Offspring of certain fruit flies may have yellow or ebony bodies and normal or short wings. Genetic theory predicts that these traits will appear in the ratio of 9 to 3 to 3 to 1. And that's broken down as yellow and normal, yellow and short, ebony and normal, and ebony and short. A researcher checks 100 such flies and finds the distribution of traits to be 59, 20, 11, and 10 respectively. What are the expected counts and what are the degrees of freedom? So what do we want to do here for the expected counts? How do we want to go about this? Got to be a little creative here. We can't just divide everything equally. We don't have 4 categories divided by 125 for each, because what do we notice here? Yeah, we got a ratio, right? So we got to be careful that we make sure we stay true to that ratio, because we're not going to expect that the yellow normal ones are going to be the same amount as the ebony short ones. There's a difference. So when we look at expected counts this time, I'm going to add up all the total parts I have here. So if I do 9, 3, 3, and 1, I come up with 16. So out of that group of 16, I expect 9 of them out of that 100, 9 out of 16 to be the yellow and normal. So now I just figure out what proportion of 100 is that. So basically I just multiply this fraction times this, and I'll get my expected value. So if you're confused, I'll show you on my calculator in just a second, because I know this is going back to algebra and not everybody's, super excited about that. So here are all my expected values. All right, so where did I get that from? All right, we figured out that 9 out of those 16 in that interval is supposed to be the first category. So what does that translate out of 100? 56.25. All right, 2 of the categories are 3 out of the 16. That translates to 18.75. And 1 of the 16 is supposed to be the rare type, and that's 6.25. Is everybody okay with getting those numbers? So every one of these problems, that's going to be the trick, is identifying the proper way to determine the expected value. Sometimes it's easy, all right? All 12 categories are equal, slice them. Sometimes we got ratios, so we got to adhere to that as our expected value. Where we would not expect in this particular situation, all of the little fruit flies to be the exact, category would be exactly the same. Okay, because then you will get bad results with your test. All right, so there's our expected counts. Real quick before we go any further, does this meet our expected counts requirement for this type of test? Yes, because they're all what? Greater than or equal to 5. Very good. So just keep that in mind, that all of your expected counts before you even start doing everything should be at least 5. All right. What are our degrees of freedom? Well, there's 4 categories. Take away 1, you're left with 3. All right, so we have all of our information. We could actually start doing stuff in the calculator, but let's set up our hypothesis test first before we get too excited with the calculations. So basically the question we're trying to answer is, are the results that we got consistent with the theoretical distribution predicted by the genetic model? All right, so there's your first part. Name of the test. We're still doing the chi-squared test of goodness of fit. We do have a random sample of fruit flies. All expected counts are greater than 5. How do I know? There they are. So you do have to identify and write out your expected counts. Don't skip that step. Now you can abbreviate. So this is yellow and normal, yellow and short, ebony and normal, ebony and short. Everybody knows what that means. That's reading this test. But I have to have all my values there to prove that I know everything is greater than or equal to 5. Nice thing is this list will be shorter, right? Because there's only 4 categories to type into the calculator. So that 12 was already harder than it needed to be. All right, let's make sure we know what our hypotheses are. So the original one is the proportions of fruit flies are the same as the theoretical model. That's what I expect to get. When I walk into a room and I experiment on fruit flies, I should expect the proportion, or otherwise it wouldn't exist. The alternative is we're going to test to see what we got and verify that at least one of those proportions is not the same. So if we can find one of them that's weird, then we can then say we have enough evidence that the original is bad. Okay, I will let you guys play with the calculations part first before I put the answers up. Oops, there you went fast, sorry. So go ahead and do the calculations and see what you get. Remember, if you're clearing your list, use the word clear, not the word delete, or you'll be crying and panicked when it comes to AP exam time. Delete will remove the list altogether, so you'll go from like L1 to L3. So there's a way to set it back, but if you're in the middle of an AP exam and concentrating on what you're trying to do, and also your L2 just disappears, then everything you go from everywhere, you have to type in L3, and I just don't want you guys to panic for that. So there's a way to get it back. I'll experiment with it later, make sure it's right. But it's happened before. Somebody's been working like, Mr. G, I was doing it, that my L3 became my L2, and then everything was off by 1 because I didn't change it, and I got errors, and my calculator broke down. And you guys already have like stress and anxiety before you go in there. So and we're just adding to it by your calculator malfunctioning at the one moment in life it needs to function. Right. If it happens to you guys during the AP exam, chuckle for a second, laugh. We've already talked about it. Everything will be fine. I know for sure, 100%, if your list disappears, you can always do second, the plus sign, and then 712. It'll just reset your calculator back to what it needs to be again, and you're good to go. Like that's the last resort. Everything's good. Now, what sucks is you have to retype your lists if you mess them up, but at least you have your calculator back to its functioning normal stuff. But I believe there's a way to fix it through the stat thing. I think if you hit stat and you go down to number 5 when you're in edit, I think that resets it back to the list. I have not experimented with that yet, so we can do that here in a second. We'll do some live experimentation. All right, so make sure you got everything in your list, run your test, see what you get for your data. And if you got your answer, then go ahead and start writing your conclusion. I'll put my final answer up here in just a second. All right, so here's our answers. Compare, see what you got. So chi-squared value is 5.6711 with a degree of freedom of 3, a p-value of 0.1288, and an alpha of 0.05. Anybody get anything different or got confused or need help with their answers? Okay. All right. There's the conclusion. Then if you need it, you guys should already have this written down, but it basically says the same thing it said before. Since the p-value is greater than alpha, we fail to reject the null. There is not sufficient evidence to suggest that the distribution of fruit flies is not the same as the theoretical model. So yeah, we got some discrepancies in our data. We got 59 instead of 56 and 20 instead of 18 and only 11 instead of 18. That one seems a little weird. And then 10 instead of 6, but they're not weird enough that we go into complete panic mode and completely change our proportions. Just chalk it up to life being random and things do what they do.
Isn't those done?
No.
Yeah, I'm trying to like.
Oh, you're still doing that? If you want to go in the hallway real quick and try it, you can. Or just pick an you just pick an object on the wall, like pick the graduate poster or something.
I picked this chair.
Okay, that works too. Just pick an item.
So how do I know if I'm doing it correctly?
You have to watch that video because Laura said I was saying it backwards, so I don't trust my information anymore. Laura's probably right. She's been in a class a lot more recently. Last time I took psychology or biology, I was your guys' age.
How do I know like I'm doing it correctly?
The video will tell you. That's all right. Like I say, every time you guys feel old, I feel old because I'm like double your guys' age now. So it's to the point where my students are half. When I first started, it wasn't the case. I'm like, oh, it's only like a 10, 12-year difference. Now it's like double. Oh, well. All right, everybody good with chi-squared goodness fit? Any questions on these? Hopefully you guys find these easy. Hopefully you're having a little bit of like phone out of the fact that this is a simplistic way to run a test and you get an answer and you're confident what you're doing and we're building that momentum into the AP exam. All right, if there are no questions, then let's move on to the next category, chi-squared test for independence. So this one's really cool if you're a stat nerd like myself, because you're going to compare two sets of data now and see if there's any relationship, or if they're just two random things. So if you're interested to find about dependence versus independence, that's what this next one is. So first couple of blanks to fill in, used again with categorical data. But it's bivariate this time, and Miss Alora has correctly identified bivariate data as two sets of data. All right, we're now looking to see if the two variables are associated, meaning dependent, or not associated, meaning independent. It's a very neat question to find out. Key phrasing that'll tell you you're doing this type of test are things like independent versus dependent, associated, related to, by, et cetera, et cetera. So we're hoping some of these key phrasing things will help you guys identify which test, because this is now what, like test number, hang on, my brain's on 4. This is like test number 10 that we talked about in like the last 2 minutes. So we have 4 confidence intervals and 4 hypothesis tests, and now these two. All right, so again, what are our assumptions and our formula and all that stuff going to be? It's going to be pretty much the same. We're still doing a chi-squared test. We're just now looking at 2 sets of data versus 1 set and its expectations.
Actually, when I
So you can do happy jumping jacks like that guy.
actually when I close my left eye, the object moves. I close my right eye, it doesn't move.
So again, according to Alora, that would mean your left eye is the dominant. That's what she's saying. I would watch the video though to make sure. Like I know that doesn't seem like an exciting alternative, but that's fine. Otherwise, you got it back. But I think Alora's right. I do. Because I was, like I said, I've not sat in the class for who knows how long. All right, so what are our hypotheses going to be? The 2 variables are independent or they're dependent. So a lot shorter on the writing, but that's all you're testing. All right, be sure to write this into the context like always. Okay, don't just say 2 variables, make sure it has whatever we're talking about. All right, so assuming that our null hypothesis is true, which we do until proven otherwise, this would be your formula that you will need to find expected counts. So I am going to do it by hand with you guys for the first example. And then yes, there is a calculator shortcut to do this for the second example. But it's important that you guys understand how this works because they do ask this stuff on multiple choice questions, either on our test or the AP exam. So just skimming over this and not paying attention to it is not beneficial to you guys. But to find my expected counts, I do the row total times the column total times divided by the table total for each of my table values. Not just once, I do this for how many different values I have. So like if I'm peeking ahead at example 4, I can already see I got to do this 9 times. Anybody who's taken IB classes or did this by hand before will tell you this is not fun. So we're just going to do it once so we can pat ourselves on the back that we know how to do it, and then we're going to move on and use the calculator. For degrees of freedom, it's a little different on this one too because we're looking at a table. It is the row, number of rows minus 1 times the number of columns minus 1. There's a way to remember this that's a little bit easier. Just cover up 1 row and 1 column and then count the number of cells remaining. That's an easy way to do it too. Now, this does not include the total, all right? So the total row, the row that has the totals in it does not count for anything. It's just there for your information only. I'm talking about actual data rows. So looking at the first one, and we haven't gotten there yet, but looking at example 4, if I cover up the newspaper readers column and I cover up the 50 and older column, I'm left with 4. Because it's the number of rows minus 1. So number of rows is 3, minus 1 is 2, times the number of columns minus 1. So columns has 3, minus 1, which is 2. So what is 2 times 2? 4. So my degrees of freedom for example number 4 here in a second is going to be 4. And so the easiest way to do it is just cover up the last of each. Make sure you're actually covering up the data, not the totals. Be careful, be careful, be careful. Somebody's going to do it. Happens every year. You know, I'm talking to you, camera person that's half paying attention. Don't be that person. Or you in class who's like, no, I won't do it. It'll be you. Don't do it. So pay attention. All right, so the following data are observed on the results of an obviously old survey to examine media preferences. We know it's obviously old because there's zero to do with phones and social media on here, so just go with it. Does the evidence support the claim that the type of media preferred and age group are not independent? Basically, what we want to know is, do younger people prefer one media over another? Do older people prefer one media over another? That's what we want to find out. Interesting survey. It's obviously an old one, but interesting. We would obviously have to change it to match things today. But we have all of this data here. We've got this number of people, the 18 to 34 prefer these types of media, 35 to 49, and 50 and older. And then we have totals on the side. So to find expected values here in a second, because we want to do all of this first before we do anything, we have to make sure that we know what we're going to be doing. So for this specific one right here, say I want to find the expected value of TV fans in the 18 to 34 age group, I would have to take this number, 101, that's the row total, times 101, the column total, and then divide both of those by the 301 here. And we'd have to do that all 9 times for each one. These numbers will change because for the 41, the column total switches to 100. We don't use the 101. All right, for number 40 down here, it's 122 times 100. So they're different every time you do it. So there's not a shortcut here. So just be aware of that. We're getting ready to do the formula. All right, if preferred media type is independent, how would we expect this table to be filled in? All right, so there's the expected values. We're going to do these by hand, but that's the answers we should get. All right, so grab a piece of paper or just do it in your calculator or whatever you want to do. Let's rock and roll this baby so you guys can see how you would have to find these out if we were doing this the old-fashioned way. And I got to get a piece of paper real quick. Un momento, Canvas people. Where'd my extra paper go? There. Perfect, just pick it, Scott. I like it, man. We need some lefties. Okay, so here's what we got to do. So for the first category, we're going to have to do 101 times the 101 divided by 301. Boom, there's our first expected value. So do that real quick. So I get 33.89. All right, so this is for the top left. I'm going to go in order from top left to rest of them. So I'm just going to go across the row. So this is for the group that has 29 in it. This is the group that has 41. Again, this is the only time we're going to do this. Okay, so I want you to practice with me just so you guys know how this works. And then we're not going to have to do this ever again. The calculator will do it from now on. So just the one time we're going to go through it because they will ask you questions, I promise, about how to do this. And I don't want you to miss that question because we got too lazy and didn't do it. All right, so for the 41 group, we now have 101 times 100 divided by 301. So we have to change numbers based on what row and what column we're in. So boom, boom, boom. So now I got 33.55. All right, for the next one, you guys can work ahead of me if you want. This number and this number over 301. If you look at example 4 in your notes, we're doing the expected values for each category. Should have my calculator on the screen. Sorry, guys. Thought it was on the screen. All right, we already know what this one is. The same number as before. We can cheat. We can cheat. We know that one. All right, so that's the first row, second row. So you can already see how unfun this is. Ooh. There we go. So for 6th period, I'll tell them I'm doing it with them, but I've already done it. So 78 times 100. Yeah, hang on just one second, you better. 78 times 100 divided by 201. There we go. Now those categories are always the same on this thing. Okay, yep, because the bottom ones are the same. Mr. G doing extra math he doesn't need to do. Oh well. And then our last 3. All right, there's all my numbers. You guys double check, shout at me if you see a difference. I did it in a very fast way. All right, so these are the expected values for each of the, we will need these in a second. Regardless if we're going to use the calculator or not, we will need these in a second. But I will show you guys that the calculator will, in fact, do them for you, but I won't show you that shortcut just yet. All right, so those are my expected values. So don't lose these. If this wasn't for pointless purposes, we're going to have to type it into the calculator in just a second anyways, in order for it to compare expected versus, or not expected, but just what we got between the two values. The other thing that it'll do is it'll do it for you once we get to that point. All right, so there's our final answers. Double check that we got it right. 3389, 3355, 3355, yes, yes, 2617, 2591 twice, 4094, and 40. All right, so we did it right. So is everybody okay with finding these by hand in case they ask you a question or needed? This is the last time you're gonna have to do it. And I know doing it this way works because Skylar proved it earlier when he goes, that looks like standard deviation, because I made you guys do it that way back in September. So it does stick in your brain a little bit better when you write it out. I know it's less fun and less exciting, but it's worth it. All right, anybody still need the expected values? Is everybody good? I'm giving Maddie a headache, so I'm gonna move on. All right, so for the next part, we're actually gonna run through the test. So this is a chi-squared test now for independence. So make sure you switch the name. It's no longer for goodness of fit. We're trying to see if these two go together. So does age and preferred media type have a relationship, basically? So what are our assumptions? Again, we have a random sample of people. Then all of our expected counts are greater than 5. Yep, I think our smallest one is 25. So we're good. Again, it's important to have these kind of listed somewhere so that you can verify that. You don't have to do it by hand every time. The calculator will show you, but it's important that you guys verify it. Don't just expect it to be that way. All right, what are our two hypotheses? They're easy for independence because it's either your two things are independent or your two things are dependent. So age and media preference are independent versus age and media preference are dependent. All right, so these are the calculations we're going to get. I'm going to show you guys how to type these into the calculator because it's going to require you to use a matrix. And I don't know if you've used the matrix before, if your algebra 2 skills are still sharp without matrices, or if you've completely forgotten about them, because I know outside of algebra 2 in a rare circumstance in another class, we usually don't use matrices. So it kind of depends where everybody's at. But we're going to get a chi-squared value of 7.4399, a p-value of 0.1144, degrees of freedom are 4. We already figured that out. And our alpha is 0.05. So write down the hypothesis. You can kind of jot down the calculations if you want. We're going to verify that we're doing it correctly in the calculator. So this is where having your expected values already figured out are going to be easy versus, that one's good there. So I'm just checking my list. Versus having to figure them out on your own. All right, so we're going to use the calculator quick. I'm going to show you guys how to type these in. You will have to use your matrices, so you have to dig up that old program on the deal. Anybody still writing hypothesis? All right. Calculator time. All right, so here's our expected values. I wrote them in a particular order because, again, it's important to make sure things match up with what we got. So this is top left, go across the first row. This is the middle left, go across the second row. And this is bottom left, go across the last row. So I didn't just willy-nilly them anymore. There's an order to my madness for a reason. So calculator time. Before we even get to our test, we got to go to the stat button. I'm sorry, not stat button. We got to hit the second button and hit the little X-1 button to bring up matrices. I know you guys haven't been here in a long time. If you even got to go here in your algebra class. Go over to edit. We're going to edit A. We have to decide what our matrix size is first before we start typing in data. So this one's easy because you can't go wrong. They're both 3s. But if you guys are curious or don't remember, it's always rows times columns. So whatever you have horizontal goes first. How many of those you have times how many you have going vertical. So you should have a 3x3 matrix, not a 4x4, because we do not include the totals. The totals are just there for us. Everybody okay with that? All right, so put your yes, ma'am. Matrix is the second button, and then this little X-1 button. You'll see it in blue there, says matrix. And then go over twice to edit, and then just do A. You can pick any one you want, but I'm just starting at the top. Got it? All right, so make A what your chart is in your notes. So A needs to be this one. 29, 41, 31, 22, 27, 29, 50, 32, 40. So 29, 41, and it goes across when you press enter. So that's why I'm doing everything in rows. 22, 27, 29, 50, 32, 40. I'll take a second, make sure everybody's good. All right, everybody okay with that? All right, now hit the second button again, hit the X-1 button again. We're gonna go and edit B. B is where we're gonna put our expected values because it needs to know what we're expecting to get. So this is also a 3 by 3. You gotta have the same size. You can't have random numbers. So you gotta have 3 by 3. This is where we put these numbers in. Again, we start at the top left, we go across the first row, middle left, and then bottom left. So there's a reason why I did it that way. So 3389 goes here. And then 3355 goes here. And then 3355 goes here. And keep going. All right, so there's my final matrix C for B. Make sure you're good to go. Don't worry, this is the last time you got to do this. Gia, I don't have to figure them out by math anymore. I'll show you in a second. Sorry there, Connor, let me help you out. Man. Yes, sir. All right, is everybody good? Is Indy's your calculator pretty equivalent to ours when it does all that stuff? Nice. We're gonna find out in a second if it does the nice trick on my show.
It's just a different,
But it's still TI, so it should be pretty much the same stuff, right? Okay, we ready to go? So we got a bunch of numbers for our calculations already that our chi-squared is 7.4399, our p-value is 0.1144, et cetera, et cetera. So how do we find it out? We go to stat, we go over to test. We are now doing chi-squared option 1, which is letter C, just a good old-fashioned chi-squared test, not for goodness of 50. So D was for the last examples. This is for this example. So I press it. First thing you're going to notice is it's got a little A and a B inside brackets. Those are your matrices. Okay, so A needs to be what you observed. That's our chart. B needs to be what we expected based on all of our fun calculations we just did. So we calculate everything and we'll find our numbers. That's it. There's our degrees of freedom. See how nice it is? So if you forget, it'll tell you. Here's your p-value 0.1143 or 44 when you round it, and then 7.439855817 is the chi-squared one. All right, so now you can write your conclusion. Yes, ma'am, go ahead. So you go to, good question. You go to tests, back to letter C. And when it gets to right here, you hit second. And then you hit the little X1, and then you can just pick whatever one of these you want. So I'll say I want to do E. Yep. All right, I got to go back to A, or it's got the wig out. There's nothing there. All right, there you go. All right, so go ahead and write your conclusion, and then we're going to go back to this calculator real quick, and I'm going to show you guys the shortcut so you don't have to spend time forever and ever and ever and ever and ever finding expected values, because that was only a 3 by 3 table. They might give a Laura a 5 by 5 table on. Yeah, she's already like this. You don't know. I don't know how mean the AP testers are going to be. So we're gonna circumvent their meanness by being efficient with our calculator. Anyways, write your conclusion, and let me show you guys how to find expected values with like little to zero sweat. All right, so since our p-value again was greater than alpha, I failed to reject our null hypothesis. There is not sufficient evidence to suggest that age and media preferences are dependent. You guys notice in the trend, it's a lot less likely you're going to find weirdness than you think. And trust me, if you're going to go into marketing, you're going to do this kind of stuff. Does playing my ad at the beginning of the hour versus the end of the hour make a difference on age group? Or does, I mean, all kinds of weird combinations you're going to look for and see if there's any sort of correlation between. Again, not necessarily causation. We're not running an experiment. We're just looking at trends and making a decision. We're doing observational studies, as it were. So all these things are wrapping in together. So we're doing observational studies. So merely we can only make a correlation reference to it. We cannot say causation, even if we did find something weird. Because it wasn't an experiment. These people already pre-chose what they were going to do anyways. So in theory, we could say, well, maybe the people we picked already liked TV more, so whatever. And everything kind of goes in circles. Now you understand why statisticians always seem so unsure about their answers, because they always know that they could be wrong. All right, you ready for the shortcut? The life-saving shortcut? All right, so if you got your calculator, the only thing you're going to have to do is when you decide that you're doing an independence test and you've got one of these little charts here, right? The only thing you have to do is go to second, go to the matrices, and all you have to do is fill in, sorry, I didn't mean that. Second matrices, all you have to do is fill in A. That's it. So just type in what your data is, 29, 41, 31, 22, 27, 29, 50, 32, 40, boom. Easy peasy lemon squeezy. You make it look exactly like your chart on your homework assignment or whatever. Then for B, I think I can just clear it. Maybe we'll see. No. Edit. I just hit clear on this. All right, let me do a real quick reset. So there's got to be a way to do this. So basically, you don't have to type anything into B. All right, so I go to second matrices. I got to type in my first list because I haven't figured out the shortcut to clear it. But I know it's a 3x3 because I'm looking at a 3x3 set of notes. So I just type in my values: 29, 41, 31, 22, 27, 29, 50, 32, and 40. That's it. That's all I got to type in. Don't waste your time doing all that math to figure out your B. Don't do it. Don't need to. You go to stat. You go over to your tests. You go to letter C for our square test. It's going to say your expected values are in B. Yeah, sure, calculator, they're in there. I promise I did all the math. It doesn't know any better. I'm going to hit calculate, and that's what I see. Same answer. But Mr. G, I didn't waste all my time putting the stuff into B. No, you didn't. But how do I know what my expected values are, Mr. G, if I need to make sure that they're greater than or equal to 5? Here's the fun part. Go second, go matrices, go over to edit. Look what's in B. All the answers already done for you. Connor's laughing. Good. If there's nothing else today, I got to smile at the corner. Right there. So really fast and really easy. You can go in there and be like, yep, all greater than 5. Yes. Now I got to hope I can figure out how. There's got to be a way to clear this. So if anybody knows that trick real quick without having to reset the whole calculator. No, it's not. Let me do it there. There's got to be a way to clear it. 1 second, Connor. I want to make sure I do this right. No, that's for something else. I'll ask Ms. Nichols. I know she knows all this weird stuff. I thought maybe clearing it would do it, but it doesn't. All right. Anyways, Connor, if I have a blank matrix C, right? I got my calculator reset. So I'll go second matrix. Just go over to letter A and just look at your notes, right? You're like, okay, Mr. G's making me do a 3x3. Right? Easy peasy. So I just do 3. You don't have to even think about it, right? Just don't include the totals and you'll be fine. And I just type in my numbers: 29, 41, 31, 22, 27, 29, 50, 32, and 4. Boom. There's all my numbers. Now I just go straight into the test. Like, don't even worry about looking at column B. So if you look, I've got 0, like nothing's typed in. I didn't even put that it's a 3x3. It is completely empty. So I go to stat, I go over to test, and I'm just going to go straight into my chi-square test. I'm going to pretend like I have nothing to do with expected values. And so all I got to do is go in there, and then that's going to be at B. So you could use a different matrix if B was already taken from an earlier problem. The good news is it's going to overwrite what's ever in there too. So if you have something like, I didn't want to mess up what we already had in there, but if I had like a previous problem stuff in B, it will clean it up and overwrite it for you. Like it's that neat of a program. So if you forget, whatever you just did is going to be B. So you don't have to worry about like, oh, is that from like the previous problem? You don't have to worry about it. So I just don't do anything, Connor. I just run the tests. All I did was type in A. It's going to give me my answers. right? There's my chi-squared value, there's my p-value, etc. If I want to go look at B, I just hit second, matrices, I just went over to the edit list, and then, oh, look at that, B's been filled in for me, there's all my answers. Lifesaver. Like, how long did it take us to do a 3x3 table? What, at least 5 minutes, 6 minutes, 7 minutes, something like that. And then I got to make sure they're in the right order. Then I got to round the decimals and make sure they're all whatever, like a lot of extra time. Then I got to type them in. What if I make a mistake and my fat finger and I put an 8 instead of a 9 in? Like all these things, right? All gone. You just do your first original list. If you can just make sure your first whatever is good, you're set for your second. So did that work on yours too? Isn't it? So again, this is a nice calculator. Love it. Okay. It doesn't have all the answers, but it can help you find them if you're smart enough to use it. So there's our conclusion, and we're done. Let's look at a last one for homogeneity. It's very similar. It's used with bivariate data. Used if two populations, to see if two populations are the same, homogeneous or not. So again, those of you guys that have done AP biology, I guess this is probably where you used it in, right? You're looking at two different populations. Are these traits the same? I don't know. Again, I haven't sat in a biology class in a long time. Key phrasing for this one: different from, difference between, is the same, etc., etc. Everything is the same as chi-squared test for independence, except the hypothesis. So you're going to do this all exactly the same way. So I'm going to be very hands-off on this one. This is our last example for the day. Make sure you guys understand how you use your calculators and make sure this works. So here's your two hypotheses that are different on this one. Are the proportions of the first variable the same for the second? At least one of the proportions of the first variable is different for the second. Again, these are in your notes. The key phrase on all these is always at least one. Be sure to write in your context. So there's your example. I'm going to take a step back for a second, grab a drink of water. You have data on drinking behavior for independently chosen random samples of male and female students. Do both genders have the same drinking habits? See, we talk about drugs in this class. How fun. Make sure you tell your friends.
What type of drugs?
Drinking. So whatever you're drinking, man.
Women will get more influence the more they drink.
Well, we're about to find out what their habits are. We don't know about the influence, but we're gonna find out about their habits. All right, so go forth and chi-square it, see what you get. I'll stop here. So you got your assumptions, hypotheses, calculations, conclusion. Give you 5 or 6 minutes. If you don't get all the way done by then, that's fine. Hopefully you get your calculations done by then. The nice thing about your program, the matrix program in your calculator while you guys are working this, if you type in the numbers weird, because obviously this is not a 3x3, there is a 4 and there's a 2. So if you type your matrices dimensions in wrong, you will see that your matrice in the graph or in your calculator looks completely different than the chart. So you want them to be the same. So for those of you guys struggling, this should be a 4x2 in your calculator. Anyways, just wanted to put that out there real quick. Yeah, don't use the totals, Skylar, when you go through it. The totals you do not type in. No, you're talking about the matrix. It should be a 4x2. Yeah, don't count the totals. The totals don't count.
Don't count the totals?
Don't do it. Yep.
It's just like correct answer.
Hang on, because I'm getting something different on my calculator than I got on my. I typed something on mine, so I'm gonna try to fix it for you guys. But yes, you are correct there. That's what I did wrong. Oh, easy fix, easy fix. And if you get a really weird looking p-value, you probably did it right. Like a really weird looking p-value.
So you want us to draw the matrices.
You don't have to draw them. You just have to make sure you label your expected values and check that they're all above
Want to
5.
know which method we use?
So I
On the test?
on the test, you do not have to draw the matrices. You just have to list off the 4. You'll see in a second when I go on the screen. You just have to list off the 4 calculations. All right, give everybody about 3 more minutes. Some people in the class have already got it figured out. I'm gonna wander around and be nosy. See what Connor got because he shook his head. He got the same weird one I got. Oh, okay. Oh, you're good. Clear? Yes. It's a weird one. I'll make it really small. Yes. So that number means that so many zeros are in front of the decimal, but minus the number. Yeah, so that looks fine. That one looks good. And p-value basically there. Is that what it rounded to? Or did they have like a really weird stuff? Rounding, yeah, rounding wise. Okay, so the official answer is like 20 zeros. It's fine. Like, it's fine. Get it? Yep. Yeah. So it's just different calculators might do it different. It's an ignorance, it's not wrong. It's times 10 to the negative 21. So there's 20 zeros in front of your calculator. Like 0. And if you guys get an extra minute before I put all the stuff up on the screen, go back and look, check your expected values in your calculator and see that they're all above 5. So now the calculator's done the work for you. You can verify before you even start writing things out that your expected values are whatever. All right, 1 more minute. All right, so like I said, for those of you guys waiting, they're almost done. The homework is easy peasy. Like it's 1 page front and back. That is it. There's no textbook. There's no FRQ yet. You guys can work on this today, the rest of the day. You can also save it for Thursday when you don't have class and you're bored, and instead of reading your social media TikTok video feed for the 55th time, seeing that there's still absolutely nothing on there that's that interesting, then you can do your homework. I'm on a secret mission to remove my wife from social media. I've almost got her. She still hangs on to the Facebook so that she can make sure to connect with family and friends, but almost got it. Because she always gets all mad when she reads stuff she doesn't like. I'm like, stop reading. Or do like I do. The only thing I have on my Twitter feed is weather alerts and sports updates. That's it. If somebody talks about something political, delete. I don't want to be burdened by that stuff. Don't care. Okay, so here is our chi-squared test for homogeneity. What are our assumptions? That we have 2 random samples of students? Check. And that all expected counts are greater than 5? Check. So that's the matrix C, I guess, if you're talking about drawing one, Skylar, that's the one I'm looking for. So this is the expected counts. Well, Mr. G, I don't want to do all that math. There's a lot of decimals. Don't. For me, this was matrix C in mind because I just went on to the next one. So I changed A to fit my new one, and then I made C my new expected value. So I can just go right in there and rewrite my expected. So this is 0 drinks or none, low drinking, medium drinking, and heavy drinking. And this is males versus females. So these are my expected values. All right, what are my hypotheses? That the proportions of drinking behaviors is the same for female and male students. And the alternative is at least one of the proportions of drinking behavior is different from female and male students. So we're just looking for any discrepancy from this. This is what we expect. Calculations, you guys should have gotten a high level of a chi-squared, 96.53, with a very small p-value. In fact, the Zindi's calculator said 0, and there's nothing wrong with that because it's 10 to the negative 21, which is 20 zeros in front of the 8. So it's 0.0000 20 times 867. Like that's microscopic p-value. Ants would think that that's small. All right, degrees of freedom, 3. So remember, take away your last row and your last column, and then what's left over? You got 3. The calculator also gives it to you, but for those of you guys that are, you know, for those of you guys who are confused, I cover everything up. I count 3, 1, 2, 3. All right, and then my alpha, unless otherwise stated, is 0.05. So hopefully you guys identify that that p-value was indeed less than alpha. Therefore, we're rejecting this hypothesis. We found sufficient evidence to suggest that drinking behavior is not the same for female and male students. Something we already know, but there you go. Now, we don't know the reason why. We didn't run an experiment to see which one's really more. We just know there is a difference. All right, guys, that's the conclusion of chi-squared. One other thing I got to show you is some linear regression again, which is going to rehash our Unit 2 memories on how to read the computer-generated charts and look at some correlation coefficients and stuff, because we'll be looking at 2 sets of data again and running hypothesis tests with that. But otherwise, you guys are now as knowledgeable as you need to be for the AP exam. Kind of scary, right? But I've already thrown everything at you. And so outside of a little bit of regression that I'm going to show you guys next Tuesday, congratulations, you've made it this far in AP statistics. Go tell your friends, celebrate, just don't drink, because you can see there's a difference. Watch out, guys. Anyways, hopefully you guys have learned some things this year. I know it's been a crazy year and weird and all that stuff, and we're not leaving each other yet. But our focus is now going to start shifting, especially after this unit's done next week, into review mode. So we're going to start bringing up stuff from Unit 1, Unit 2, Unit 3, Unit 4, everybody's favorite probability stuff, right? Unit 6, the hypothesis, all that's going to be, now we're going to put it all together. We know everything we need to know, and we'll be all set there. So AP exam for seniors is, or the paper version is still scheduled for May, and the